Welcome everybody to the first physics colloquium of the new year, 2013. It's my great pleasure to introduce Eric Mazur from Harvard. Eric did his undergraduate work at graduate work in Leiden.
Yes.
In Leiden.
Undergraduate.
Undergraduate and graduate in Leiden, and he came to Harvard in 1982. Which was the same year I was doing my last year there. He was, I think, on the floor above me or below me. We never met at that time. Eric's done a lot of work in fundamental optics and using femtosecond laser systems to study things like black silicon, as well as nonlinear optics at the nanoscale, make silica nanofibers and things like that. He's well known for that. He's also well known as an innovator in education. And he's done this for a long time. Eric has given 4 talks here over the past decade and a half. We were discussing a talk that he gave in our department as a physics colloquium in 1997, and it turned out he looked that up on his iPhone, and it was only, it was 15 years to the day yesterday that he gave that colloquium, and that was on peer instruction. And so Eric talked about his book on peer instruction. He was invited by Liz Simmons at the time that many of you will remember. And I think one of the things that he was impressed with today is how far our department has come in those 15 years in using a lot of interesting pedagogical things. So we'll hear about his work lately in pedagogy, and please welcome Eric.
Thank you so much, Bennett. One small correction. Two small corrections. I came to the U.S. in 1982, indeed, for 1 year. It's just been a very long year. I'm still here. Secondly, it's 16 years ago. This morning we were talking about 8 years ago, which shows how time flies. Well, I'm really excited to be talking about this subject. I think the last talk I gave here 3 years ago, actually at the Photonics Center, was on my research on photonics, so it's great to be talking about education, especially now. It's such an exciting time. We come from an age where information was mostly static, maybe evolving slowly, curated by libraries and universities, and only accessible in certain places, to an age where information is constantly changing, available around the clock on your hip, so to speak. So we know that education is going to have to change. It's just not quite clear why. How, I mean, but why if. Okay, so I resurrected this picture that I used in my talk 16 years ago, because for close to 20 years right now, I have been hammering relentlessly on one and the same message, namely that lectures, including the one I'm giving to you right now, right here, essentially focus on the transfer of information. I usually, when I did the talk that I gave 16 years ago, which I've probably given close to 500 times, I won't give it again today, don't worry. I usually ask people to characterize the activity that is taking place on the screen behind me. I don't show those arrows, right? And people will say talking, or note-taking, or sleeping. Yeah, sleeping, that's kind of an offensive statement, right? These are my students. This is me teaching, actually, my pre-med physics course many, many years ago. It's an old picture, BC, before computers. You see, I'm using an overhead projector. Now, I want to briefly show you some data that were obtained at MIT that relate actually to that word sleeping. Whenever people used to say sleeping, I always quoted the French writer Albert Camus, who once said, "Some people talk in their sleep. Lecturers talk while other people are sleeping." Well, let me show you some really exciting data that were obtained at MIT. This was an article that was published by Rosalind Picard, who is a professor at the Media Lab. Her group developed a sensor that can be worn around the wrist that measures electrodermal activity. The article basically talks about the electronics for this sensor. She's actually commercializing it right now. And actually devotes most of the article to correlating electrodermal activity to brain activity. So they did both EEGs and measured the electrodermal activity here and found a very strong correlation, which is not that strange because you basically measure neural activity around the wrist and, neurons are connected to the brain. And they show data collected on an MIT student during a 1-week period. Why is this wrist sensor interesting? It's interesting because it's unobtrusive. You wear it like a watch. And you can give it to a student and have the student walk around for a week and then download the data and see the brain activity over a prolonged amount of time. Yes, you could do that with an EEG, but you'd look quite nerdy walking around with the electrodes on your head. Maybe an MIT student wouldn't notice, but anyway. So I want to show you the data. Oh, by the way, the message that I've been hammering on for 20 years is it's not the information transfer that is important in education. And let me actually show that that information transfer is not working that well using data that I did not have access to 16 years ago when I spoke about the lecture. So here you see on the horizontal time. For some reason, the day at MIT starts at 4 o'clock in the afternoon. Don't ask me why. Right? Up to 15, 3 o'clock. Day 1, day 2, day 3, and you can see periods of high electrodermal and therefore brain activity and periods of lower. Now, they also asked the students to keep track of their activities, and this is probably too small for you to read, but that's quite all right. You see things like homework and chores and so on. I want to draw your attention to the parts of those traces labeled class. The trace goes flat. Now compare that, since we were talking about sleep a moment ago, compare that to what happens when students are actually sleeping. In other words, the students, at least these MIT students, are much more active, have much more brain activity when they're asleep in their bed compared to when they're asleep in class. Now, people know sleep is very important, right? There's a lot of brain activity in REM sleep. You transfer things from short-term memory to long-term memory. But that brains are so inactive during class is kind of surprising, especially if you're teaching. But if you stop to think about it, what is happening there? Your mind is held captive by the presenter. There's this continuous stream of information. There is no time to think or to make the mind wander. Our brains are made to wander, to think about things. Learning happens not when you just take information into your brain, no. Learning starts when you think, I wonder how this works. You have to have time to make the mind wander. Well, in a lecture class, and even in this lecture right here, right now, there's no time to think, because if your mind starts wandering, you start to think, you cannot at the same time process the new incoming information. Our brains are not wired to multitask like that, so you lose track. There's one activity, look at me, not at the screen. There's one activity that matches class. Think about it. Don't look at the screen. I'll show you the screen. You can look at the screen in just a second. Look at me. What do you think that is? Watching TV. There you go. Watching TV. And this is something, of course, that was known a long time ago because people did EEGs on people sitting in front of the TV and noticed that the brain basically goes into a meditative state with mostly alpha waves. Because same thing. There's this continuous stream of information. There is no time to think. No time to think. Your mind is held captive. So if you stop to think about it, why would class or a lecture actually be that different? I was really happy when I saw those data because they reinforced something that I had sort of intuitively been thinking for a long time. We have to create opportunities for students to think, not outside of the class, but in the class, which is why I started doing interactive teaching a long time ago. Today, I want to focus on another message, however. I want to focus on the following message. Let's not abandon the scientific method when it comes to teaching. I joined the faculty at Harvard in 1984. At that time, the physics department was relatively small. We had only just over 20 professors. Quite a few Nobel Prize winners at that time. For those of you who may remember the physics department then, I think something like 6. So it was for an assistant professor, it was a very intimidating department. During faculty meetings, occasionally, which we had every week in the faculty club, we'd talk about education. And in hindsight, it's actually appalling to realize that most of those discussions were completely anecdotal. My students learn better when I do this or that. Or my students like it when I do a lot of demonstrations. Fine, if they like it, they actually learn better. Right? We should actually treat our approach to teaching the same way we treat our approach to doing physics, and collect data and use the data to inform the decisions we do in the classroom. I love to rub the next quote from Lee Shulman, a professor at Stanford and former president of the Carnegie Foundation, in the face of anybody who uses anecdotal evidence when talking about teaching. Oh, this was there already. The plural of anecdote is not data. In other words, you don't validate an argument by just giving a lot of anecdotes. And in a sense, I see my classroom as an extension to my laboratory. In the laboratory, I collect data on the interaction of light with matter. In the classroom, I collect data on how students learn and how effective different approaches are. Now, I showed some data 16 years ago on the effectiveness of interactive teaching. If you haven't seen it, it's online. You just type in "Confessions of a Converted Lecturer" and you'll find what I think are pretty convincing data that interactive teaching accomplishes a lot more than just passive lecturing. Today, I want to just show a few other projects that I don't get to talk about as much. And there are basically 3 different research projects that we ran, 2 of them published, 1 not yet published, although they are in a thesis, that we did in the classroom. 1 relating to gender issues, another relating to the effectiveness of classroom demonstrations, and a 3rd one relating to the role of confusion, which actually brings us back to what I said before about thinking and about learning by first wondering about something. So let's start with gender issues. A number of years ago, at the University of Minnesota, they saw that there was a distinct difference between the performance of male and female students on an assessment instrument called the Force Concept Inventory, FCI, post-test, meaning at the end of the semester, was the men outscoring the women. Now, the FCI is a very basic assessment instrument that, using a series of about 30 questions, tests students' understanding of the concept of force, which is, probably the most basic concept we have in a physics course. And it tests that not by asking students to solve textbook problems, it asks that by asking word-based questions. If you understand the connection between force and acceleration, and Newton's third law, and other basic principles like that, the force concept inventory becomes almost trivial. In fact, most physics faculty, when looking at the force concept inventory, will say, this is too easy for my students. That's certainly what I said when I first saw it. And then I gave it to my class, and oh, horror. Hardly had to start taking it, or one student said, how should I answer these questions? According to what you taught me, or according to the way I usually think about these things? And then you discover that your students actually still think there's a relationship between force and velocity, and that heavier objects exert larger forces on lighter ones than the other way around. Well, I saw that, and I thought, well, it would be interesting to actually study what causes this gap, if we can, and if there's a way to actually mitigate this gap. So I started to, since I had already many years' worth of data, I was first curious to see how it was in my own class at Harvard, and we collaborated with on this project with Worcester Polytechnic Institute, so we asked for their data as well. So thousands of students over many years. Here are my two Harvard classes. One is a pre-med class and the other is an engineering physics class, and you can see that the gap always hovers around 10%. So there's no difference between University of Minnesota, Harvard University, or Worcester Polytechnic Institute. There's the same gap. So first question one might ask is, what causes this gap? Well, I already told you, I like to treat my classroom as a laboratory. Likewise, when I go on a sabbatical and I'm in another environment, I like to see if I can get data in another country. So I decided to see if I could get some data from other countries. Here are the average of all of the US data that I had before I left. I went to, first to a country in Northern Europe, which I won't name, a very well-respected engineering school. I tried to convince a few colleagues there to give the test. It was in a Dutch-speaking country. It was not Holland. Well, you know now which country it is. The reason I'm saying that is because I want to make sure that you understand that the translation in Dutch was correct. It's my mother tongue, so I could make sure that the Dutch translation of the FCI was not measuring something different than the English, and that language was not a barrier. I had two expectations. One is, or at least one expectation, namely that the students in Northern Europe would do significantly better than the students in the US, even Harvard. Why? Well, because I made a mistake. I made an assumption that I think we all tend to make. We tend to project our own experiences onto the world around us. I had learned physics in Holland, and therefore I thought the people around me had learned physics just as well as I did. Therefore, surely, you know, the Northern European countries had to be better. Well, it was a disaster. The dean of the university called me into his office and said, "You're never going to publish these data or show them." But even more interesting was the gender gap, which was significantly larger than in the US. Then I went to Taiwan, did the same thing. The first 4 or so of my graduate students all became professors at Taida, Taiwan Daxue, which is the Taiwan Normal University, which is their flagship university. And when I came up for a sabbatical, I said, "Why don't you come and spend it with us?" And after arriving there, I said, you know, it'd be great if we could give the FCI to Taiwanese students. I mean, that university, Taiwan Normal University, produces a large fraction of the graduate students we get at Harvard. It's a you know, very strong university in terms of the sciences. Well, they showed the FCI. They were junior professors at that time, so they couldn't take the decision. They showed it at the department chair, who looked at the FCI and said, "Are you crazy? This is too simple. We cannot give this to our students." And then my students said, "But they're doing it at Harvard." Well, I plummeted in, you know, the respect I got was much less after that. Fortunately, near Taida, near Taiwan Normal University, is another university called Taiwan National Normal University, which is focused on teacher education. And there they were very interested. So my graduate students helped translate the FCI in Chinese. No, the university translated in Chinese. My graduate students translated back from the Chinese translation to English because I wanted to be sure that the questions still adequately reflected the original ones. And we gave it to the students. One did it quite well, not excessively so, not better than Harvard. The average is about the same. But, and this is really interesting, there was no statistically significant gender gap. Now, I was not able to research what really the causes are. I can only speculate here, and I know I just said something about anecdotal data, so I should be careful here. But But the differences that did stand out between those three environments were, one, in Taiwan, there were as many, in that particular university, there were as many female professors as there were male professors. In Belgium, there was not a single female faculty in the physics department where the test was given. No role models whatsoever. In the US, it's about a quarter. So maybe that the environment matters. But something that is very clear here is that there's no reason for the gender gap to be there. If it can be absent in Taiwan, then it should be absent everywhere. What is the effect of pre-college education? And here we go back to my data at Harvard. If you look at the performance measured depending on the FCI pre-test, right? So this is on the first day of class at the college level. For students who have not had any physics, you get about an average of 35. For students who have had high school physics course, it's somewhat higher. For students who have had AP, it's even higher. I'd expected a little bit stronger correlation, especially if a student has taken the AP, and most students who take the AP and come to Harvard have a 5 on the AP. You would expect them to at least have mastered the concept of force, right? Unfortunately, that does not appear to be true. What about men? Well, you see that there's a gap, and the gap persists across education. Men and women go up, but the difference remains. And even worse is that women tend to be underrepresented at the higher level. So they're about this at Harvard, in the Harvard population, about the same number of women here and here, but there are far fewer women who have taken the AP physics course. So what can we do? I mean, of course, I can't change what happens before they come to my classroom, but maybe there's something I can do in my classroom to mitigate that gap. And there's plenty of evidence that women tend to benefit from a collaborative environment rather than a competitive environment, and from one that involves a lot of verbal discourse. Now, for those of you who don't know what I do in my classes, about 20-some years ago, I instituted the instruction where basically I don't teach by telling, but I teach by questioning. Instead of focusing on the information transfer in the classroom, I have the students either watch a lecture of me before coming to class, well, I ran the same lecture year after year anyway, or read the book. And then in class, I teach by questioning. I walk to class, ask the first question, talk a few minutes, ask the first question. Student, think about the question. They commit to an answer. Some of you may be familiar with the clicker, which started a few years after I started with the instruction. Then I ask them to turn to their neighbors and convince the neighbor of their answers. In essence, they're teaching each other, and I call them again, and then the cycle continues until the end of class. Well, I thought the collaborative aspect of this approach, as well as the verbal aspect, might help women. So let's see if increasing the interactivity and the collaboration does anything to mitigate this, this gap. So basically I'm going to show you data collected over something like 15 years, comparing traditional lectures, on which I have data, comparing interactive lectures, the way I just described it to you, to interactive lectures plus making all of the other components in the classroom also interactive. Rather than having teaching fellow, in essence, lecturing to the grad students, we make it interactive activities. We make the homework even collaborative. So 3 different approaches: T, traditional, I, or IE, interactive engagement, and IE plus for even more interactivity. So here, for the 3 different treatment groups, T, IE, and IE plus, the pretest, remarkably stable for the women. Which just means that the admissions office at Harvard does a very good job of picking the same type of students, I guess. And I'm going to remove the pretest data. So that little triangle gives you the average pretest for the female students. The male, there's a little bit of variation, but the variation actually happens to strengthen my argument here. But we're going to again take the average. That little triangle on the far right gives you the average pretest for the men. So now let's look at the post-test. Here are the women, clearly gaining from the interactivity. which in a sense is the data I showed you 16 years ago. The men also gain, right? Each improvement improves the performance of the men, but the women gain disproportionately more, eliminating the gap because at the highest level, the gap is no longer statistically significant. Let's actually look at not aggregate data, but individual data. So we plot for each student the pre-test score on the horizontal scale, and the gain, in other words, the difference between the post-test and the pre-test on the vertical. So this is a student who started at 90 started at 70 and ended at 90 on the FCI. Here are all of the female students in a particular class, and here are all of the male students. And again, this is in a given class taught using traditional teaching. If you look below the median, you can see that there's an imbalance in gender. There are more female students than male students. If we go to an interactive class, you see that all of the data move up, meaning a bigger gain. And if we look now below the median, we see that, or at the lower end of the class, we see that there are actually maybe even more men than women. So clearly the interactivity helps improve or helps address this imbalance in the gender. So points to keep in mind from this part of my talk is that, and feel free to ask me questions at any time, we don't have to wait till the end. The gaps come from the culture, the background. There's no reason for it to be there. But the good news is we can actually help address this imbalance by bringing a collaborative atmosphere and the interactivity back into the classroom. I don't know, did I have the reference? Yeah. If you download my slides, you can find the reference to the paper that we published, which is in the American Journal of Physics in 2006. So, that's the first research project. Yes?
So just a question on this. Have you studied whether or not your groupings or the interactive subunits, if they are gender segregated, does that make a difference versus non-gender segregated?
Right, so when I ask a question, after the students commit individually, initially I just said, talk to your neighbor. I didn't give any further expressions than that. We tend to be very social people. Chances are that you're sitting here next to somebody you know, maybe somebody who works in the same group, or somebody you take a course with, or a colleague in the same area, or the same department. Students are like that too. They tend to sit next to their friend, and when they say talk to each other, they tend to select somebody they're already comfortable talking to, which is not necessarily the person they're most likely to learn from. We did not study, it might even be a person who gave the same answer. I've been surprised at how many students will talk to somebody who has exactly the same answer and say, oh, you got the same answer, must be right, let's talk about something else. So now my instructions are a little bit different. Find somebody who has a different answer. If the person next to you has the same answer, say thank you very much and turn to the other side of the front, or get up and walk around. However, what we're only finding now, and those data are not in that paper from 2006, because we haven't published this yet, is that the self-pairing is very ineffective. Students tend to not choose their discussion partners effectively. So now we actually have a new research project. We're actually studying what constitutes good pairing. First of all, is it 2 students, 3 students, 4 students? Should it be 2 different answers? Should there be at least 1 correct answer in the group? What about gender? What about other underrepresented minorities and so on? We have some data on that. There's a thesis by Jessica Watkins in my group who studied underrepresented minorities. But we still have a long way to go there. Now,
what happened at Wellesley College?
Worcester Polytechnic.
Wellesley.
What happens at Wellesley?
Wellesley.
When? How?
Well, the reason why, do women...
Oh, I see. What happens in
women to talk?
Yeah, I don't know. It would be interesting to study.
What's their FCI?
That's what I thought you were trying to do.
No.
That's what I thought you were trying
Okay, so what happens in an environment where, you know, you have only one gender. In fact, I'm speaking in Saudi Arabia in 2 months on gender issues. I hope I'll be able to come back alive for a huge education conference, and we'll see. I don't know the answer to your question. Okay, I'm an experimentalist. I love doing demonstrations, and my course, when I started teaching in the mid-80s, were exactly like Walter Lewin's course. I would go on a fire extinguisher propelled car from one side of the lecture hall to the other. I would hoist myself with a system of pulleys all the way up to the ceiling of a classroom that's at least 3 times as high as this. You know, everything. And I shoot the monkey I would do with real powder rather than a spring-loaded gun, and so on. I mean, it was a showman aspect to it. But the question is, how much do students actually learn from these demos? I visited once the Education Research Group at the University of Washington and was present at a thesis defense where the student presented, the PhD candidate presented results from interviews with students that have been taken at the end of a physics course, where she asked the student to explain certain concepts and to provide the memory of things that had happened in the course. And in one passage, there was a student who said that she had observed the shoot the demo monkey, the shoot the monkey demo, where you basically aim a gun. You know which demo I mean, right? You drop it. In the interview, it became clear that she was convinced that the person who had done the demo had aimed below the monkey in order to hit it. Whereas the whole point of the demo is, no, you aim exactly at the monkey, and because the monkey falls at the same time the bullet starts to fall, they hit. So I thought, wow, it's amazing how people's memory can get adjusted to what they think. And I thought it'd be good to actually do a study. Are demos simply entertainment? And I don't want to diminish entertainment. It does play an important role. It might play a motivational role. But are they also of pedagogical value? One thing is, you see me actually do a demo there, which I did the first time I taught E&M. You have light bulbs either parallel or in series, and sometimes you close a switch. I would notice very quickly that the students would not find these demos very interesting. Right? I mean, you have that demo, you close the switch, one light bulb goes a little bit brighter, most students just sleep. So now what I do is, I hide this board behind the podium, and then I put up a question that is exactly that circuit, and I have the student think about what's going to happen when you close a certain switch. Then they click on the button, then they talk to their neighbor, they click again. And then I say, look, I have this demo here, and I take the demo, it's exactly the same as on the question I just asked, let's see what happens. I put my hand on the switch. They're all focused. I mean, the whole classroom goes quiet. I close the switch, one light bulb flickers a little bit, and I get this huge cheer. It's amazing how by engaging the brain, a demo that normally is totally uninteresting can become much more captivating. But anyway, this is what we decided to do. We decided over a 2-year period to split the classroom in 4. We had 250 students, so each group had a little over 60 students. One group would not see the demo at all. This was our baseline, with no demo. In the second group, we just asked the instructor to do the best possible job showing the demo in the Walter Lewin or old-fashioned Eric Mazur type approach. Just do the demo, explain everything, do the best possible job explaining it. In the next one, we asked students to predict the outcome of the demo before seeing it. So before we did the demo, we had a question, they had to think, and then vote on it. In the last one, we gave the students a worksheet, which at the top described the demo, then had the students, in a free response question, explain what they thought would happen when the demo would occur. Then we did the demo, and they had to describe their observation, and they had to check a box. My prediction does check or does not check correspond to my observation. And after that, they had to, in little groups, reconcile any discrepancy between observation and the demo. And of course, we varied the group. So, you know, we would take the students. In 1 week, this might be the no demo, and that's the observe, predict, and discuss. But then we rotated the modalities among the different groups to equalize all of the data. Yes?
I'm a little confused. The first thing I would think takes 2 minutes in my class. The second thing takes 5 minutes. The third
Did you see my
takes 10
slides?
minutes.
You must have downloaded my slides before. So there is a time difference, right? There's certainly a different time investment. The no demo takes no time at all. The observe takes whatever time the demo takes. Predicting them beforehand adds 2 minutes. And discussing adds 8 minutes. So there's certainly a time investment, thank you for between the different modalities. Yes?
Oh, where you did the discussion, but just told them the answer or showed them a slide.
A big time?
You could imagine just skipping the demo altogether, doing the last thing, and just showing them a slide instead of doing the acts. What purpose does the actual demo serve as opposed to just a slide that does the same thing with all the
Let's see. Yeah, absolutely. In fact, you know, that's what we do all the time because there's so much teaching that goes on without any demo at all. In fact, I would argue that's probably what we do all the time. Let's just tell them what happens, right? Okay. So we followed up with a free response test online, and I'm going to show you the result. And then we had a number of exam questions, because I would argue, which actually connects to your question, that the true hallmark of learning is being able to take something you've learned and apply it in a new context. Right? If you're unable to apply something in a new context, you have not really learned. However, most of teaching, going back to that picture that I had before of the information transfer, is the instructor transferring information to the students, and you wait a month, and on the exam, the students just give the information back to the instructor. Not that long ago, I was actually giving a similar talk at the University South of Boston. I won't name which one. And after my talk, in the physics department, after my talk, one of the professors came to me and said, I had something really interesting happen in my course this year. He wanted to make physics relevant to a student, so he had put it in the context of something that was meaningful to the students, and the context he had chosen was baseball. I mean, there's a lot of physics in baseball, right? Trajectories of balls, collisions between bat and balls, runners running, you name it. So in class he used baseball examples. On the homework, there were baseball problems. On the midterm examination, there were baseball problems. At the end of the semester, he was preparing the final exam, realized he'd run out of baseball problems. So he put some football problems. The professor complained to students, we've never done any football problems. So I think, stop to think about it, right? I mean, you laugh because it probably resonates, either as a student, the discomfort of having to apply something in a new context. If I have a student who comes to me after an exam and tells me, Professor Mazur, I've never done a problem like that, I tell the student, look, if you had done a problem like that, it would by definition no longer be a problem. Right? A problem is not knowing how to do something. And so much of our assessment, I don't want to get sidetracked too much, so much of our assessment is focused simply on the outcome, the answer. There's a real problem. You know the outcome. It's how you get there that is important. Okay, so that's why we put in exam questions that change the context, but really tested the same concept. So here's a demo, loaded beam demo. You have two scales. It's not a very exciting demo. Two scales, a plank, an object in the middle, and you ask what happens when you put the object on one side. This is used in the context of torques. Right? So you have to take those forces and torques into account. It's a very common misconception among students, believe it or not, that it doesn't matter where you put it. Right? Because each is going to have half of the weight. The plank evens out the weight. So we did the demo. We asked the question, we asked for the students' predictions, and we did the demo, and we did it in the 4 different modalities. The online test question, which came a month and a half later, was numerical. It had this figure, and the students had to fill out what the question marks were. So this is memory, in a sense, and this requires you to extrapolate to a situation not seen before, and you calculate the torques. 24% of the students gave the right answers and correctly mentioned torque in their explanation. Another 38% gave the right numbers, but used mostly proportional reasoning, so it's hard to judge. Depending on how harsh you want to be, you can say either 24 or 24 plus 38% got the answer correct. I would argue only 24% got the answer really correct. 20% of the students, 20%, said it's independent of the position. I went, wow, that must be the 20% who did not see the demo. But then we looked, not at all. In fact, some students wrote down, as shown in lecture, it doesn't make any difference where the block is put. The plank evens out the load. I got so excited. I ran to a colleague in the psychology department and I told him, look, I just found something really interesting. And he said, what is it? I described it to him. He tapped me on my shoulder and said, Eric, we've known this all along. I was very disappointed, and you can see my disappointment. So he asked me, why do you like physics? I said, well, I like physics because I don't have to memorize very much. I can just reason my way through things. He said, exactly. Imagine you're a student who has this incorrect mental model. The plank evens out the load. Now you come to class, and the professor does a demonstration in front of you. And you see one scale go up and the other go down. You have what Piaget calls a cognitive dissonance. You go, whoa. Maybe you quickly scribble it down in your notebook. Before you have time to think about it, the professor continues to talk. Not giving you any time to reconcile your incorrect model to the observation. And unless you have another opportunity to change that mental model, what the brain does, and psychologists have known this for a long time, is that you adjust your memory to the incorrect model. Magicians, politicians, lawyers at trials, they all try to put the wrong model into your head because that adjusts your perception of it. So instead of teaching the students something useful, you actually reinforce the role model, right? Think of that student, or those students who wrote down as shown in class, right? Not only do we have the role model, now they use their adjusted memory as evidence that their model is correct. 10% of the students give quantitative reasoning, and then there's another 6% where the forces don't balance, it doesn't add to 20 anymore, and 2% other incorrect answer. Let's look how it's between correct and counting correct. Only somebody who gives the right numbers and the right reasoning. We see those percentages. I want to draw your attention to the observe, the lowest of all. Now, it turns out that was only for this particular demo, but that sort of shows that just observing can actually be harmful if you don't get an opportunity to adjust your mental model. You can actually build a wrong memory in your mind. Anyway, here's the exam question that shows students' ability to transfer the concept. It's exactly the same idea, but now we've replaced the scales with ropes. A uniform plank is supported by 2 ropes at point P and Q. The tension in the rope at point P is 150 Newton. So that means the other rope must also be 150 Newton, and the total weight of the plank is 300 Newton. Now suppose that that rope on the right is moved to point R. What are the tensions in the 2 ropes? Okay, so same thing, you need to balance both forces and torques. So 36% gets the right answer, including the correct reasoning, which is a little bit better than on the online test. 13% of the students has 150 and 300, or 75 and 225, which results from incorrectly considering the lever arms. But then, as I was grading this problem, I noticed that a number of students had really weird answers. 112.5, 16 students, or even more, because there are 250 in the class, so some 20 students. 112.5 and 187.5. And some had 112.5 for both, 2 or 3 students. Any idea where that comes from? I quickly figured out that 112.5 was 3/8 times 300. And 187.5 was 5/8. But where do the 3/8 and the 5/8 come from? You know, I was grading this, I was keeping track of all of the different answers, and I couldn't figure it out. And any of you? I finally did, because one student actually articulated.
From the 5 and 15.
Nope, not from the 5 and 15 in the demo.
What was the distance that you gave for QR as a fraction of 2?
This is a quarter. This is a quarter. But you're getting there. Here's what they thought. Let's just split this in 2, right? This part is supported by this row. Since this is a quarter, that's 3/8. This is 5/8. And here, you know, this is sticking out, so it doesn't need to be supported at all. Who would have thought? That shows what Steve Pinker calls the curse of knowledge. Right? Once you understand something, it is very difficult to reproduce or think the same way a beginning learner does. That's what makes it so incredibly hard to teach. And the better you know something, the harder it is to address the misconceptions that the beginning learner has. Yeah.
Correlation between the online assessment and the exam.
I don't know. I don't even know if we ever did that. It would be interesting to, yeah, that would be interesting. They were given pretty close to each other. I never did that. Interesting point. I still have the data. Totally do that. Okay, so over 2 years and many demos, these are the data that we got. The correct answers go up a little bit with engagement, but not that much. The reasoning goes up very significantly, improves significantly. If you, oh, sorry, this is just for, no, this is the exam problem. This is the aggregate for all of the demonstrations that we measured over 2 years. And you can see that the students' ability to predict the right outcome goes up. An explanation, if we use the top one as a baseline, this is what you see. You see that the ones who observe have about 15% better ability to remember the outcome, or to reproduce the outcome, whatever way you want to say it. But it goes up significantly. If you look at their ability to explain the physics behind it, it's even much stronger. And in fact, you see that just observing the demo does a very poor job. So my conclusion from this was that at a minimum, if you do a demo, right, if you do a demo, just observing it is not very helpful, but just investing the 2 minutes to giving students a chance to think about it before you show it is something you should definitely do. Whenever you do a demo, think about it. Whenever you do a demo, give the students a minute or what, something like that, to think about the demo before they see it. And it makes sense, right? Because if you think about it, and then you see something that doesn't correspond to what you thought, you're primed to do something about it. You go, oh, I better think about this. Right? There's a sort of a red flag that went off. When you want to invest the additional, to get back to your question that you asked in the beginning about time investment, when you want to invest the additional 6 minutes for the discussion, is questionable because the improvement then is not as large. So demonstrations without engagement are not really very helpful. They might be entertaining, but they're not really authentic learning experiences. But by just having the students predict the outcome, which doesn't take very much time, you can significantly improve the outcome. Okay. Confusion. You know, I think instructors typically are praised for clear lectures. I would be surprised if the student evaluation of teaching here at Boston University did not have a question, Professor gives clear lectures as one of the evaluation criteria. Is that right or not?
Yes. It's lecture.
Right. We get praised for that. However, and you know, in general, I would say confusion is something that is discouraging, right? I mean, nothing is worse than going to a lecture and walking out confused. But on the other hand, there's the saying that says to wonder is to begin to understand. You don't learn by just taking the information, putting it in your skull, and then regurgitating the information in. You have to go, how does this work? And then go, oh, yeah, there has to be this moment of wondering and then reconciliation, which I argued before, there's not really an opportunity for in a standard approach to teaching, in a lecture approach. And the question that was prompted, I'll tell you in a minute about what that was prompted, is that I'd like to address here in the last 10 minutes, is does confusion indicate a lack of understanding? You see, a number of years ago, I started to implement a technique called, or you could take that question and invert it, right? Does lack of confusion indicate understanding? I started to implement a technique called just-in-time teaching. Just-in-time teaching is a technique that helps your student prepare themselves for a lecture that is interactive. I would give my students a reading assignment, say, read chapter 32 in the book. And I would then ask the students 2 questions on the content. They were not the type of questions that you can just look up. You cannot have the book open and say, oh, the answer to that question is here again. No, you have to actually think and transfer what's in the book to a new context. Most students cannot do that. But I tell them, look, it doesn't matter. The only thing that matters is that you have to convince me through the thought you put in your answer that you've done the reading. Right? So that's the purpose of it. The understanding takes place in the classroom. And then there's one feedback question, which is always the same. Please tell me what you found difficult or confusing. So before class, I press on a button on my website, I get the pictures of my students with their names and what they find difficult or confusing. And I got some sort of weird feeling. I saw that some of the best students in the class were the ones that expressed the most confusion. And then I would get a student who I know was really poor who said, everything is clear. So I thought, it would be nice to actually correlate that. Just let's get data and see. That study, by the way, is still in progress, so we haven't published this yet. So let's analyze this question of both understanding and confusion. Let me give you an example of a reading assignment. So this is a chapter on fluid statics, and then the 2 content questions are: consider the capillary rise of a liquid in a glass tube. How does the pressure at point P outside the tube at the surface of the liquid compare to the pressure at point Q at equal height? That's question 1. Question 2 is, 2 identical balloons are connected to a tube as shown below. Balloon B is inflated more than balloon A. Which way does the air flow when valve P is opened? Incidentally, Laplace's law tells you that the curvature is related to the pressure difference. Therefore, this smaller radius of curves has a larger pressure differential, and therefore a higher pressure inside this balloon than inside that one. You can sort of, conceptually understand that because the elasticity of the membrane, it's more curved, so the forces are pulled more inward, right? If you take a point here, it pulls more. And you know it. If you take a balloon out of the bag and you blow on it, in the beginning you have to blow much harder than once there's some air into it. So this is a great demo to do in class because you open up this valve and the little balloon empties in the bigger balloon. This was in a class for pre-meds. I'd chosen a book, some of you may know that, Sternheim and Kane, which does a very good job connecting physics to medicine. And in this chapter, it talks about the alveoli and the what? babies that are born prematurely, before 22 weeks of gestation, do not have a surfactant in the lungs, called pulmonary surfactant, that evens out, or that lowers the surface tension of the alveoli. As a consequence, the little alveoli empty out in the bigger alveoli, and you get terrible lung damage and death. So medically, this is an important thing to understand. Likewise, capillary rise is, of course, also, and Stern and Kim does a great job connecting capillarity to blood vessels and so on. Okay, last question. Please tell us briefly what points of the reading you found most difficult or confusing. If you did not find anything difficult or confusing, tell us what parts you found most interesting. You need to add that last one so that you can't just write down everything is clear, right? If everything is clear, you have to say this or that is interesting. Let's look at two examples before I show you the total data. Capillary action is due to cohesion between water molecules and the adhesion of water to the surface of the glass tube. A sentence picked straight out of the textbook. Negative pressures can result from cohesive forces of water. Another sentence from another part of the textbook. I cannot follow the thinking here, but you know, they're correct. I don't know what the logic is. At the same height, the pressure inside the tube is much less due to negative pressures. Sorry, that's wrong. Second question. The air flows from high pressure to low pressure. That's right. The fully blown up has higher pressure, than the half blown up balloon, so the air flows from the fully blown balloon to the half filled balloon. Third question. Nothing was difficult or confusing. The sections on the surfactant in the lungs and the heart as a pump were interesting because they relate physics to biology. So the student had actually read about the surfactants in the lungs, right? Here's another one. The water rises because of an interaction between the water and the walls of the tube. Notice that that's the same sentence as the other, but the student has now expressed it in his or her own words. This interaction creates an upward force which causes the water to rise, the negative pressure, right? The force is due to surface tension between the water and the walls of the tube. The pressure at the point inside the tube must be the same as the pressure at the point of equal height outside the tube, because if there was a pressure difference, then there would be a net flow of water into or out of the tube until the pressure was equalized. Fantastic! Correctly argued, the student's own words are beautiful. Second question. Laplace's law tells us that it requires a greater pressure difference to maintain a small sphere than a larger one. So the pressure in the small balloon must be greater and the air will flow from the small balloon to the larger one. Fantastic! Now look at the third question. I found the explanation of Laplace's law to be inadequate. And while I can understand the conclusion drawn, I don't understand the reasoning which led to the conclusion. There was not an attempt to explain how there's a bigger curvature, there's a bigger inward force. It was just a jumble of equations in the textbook. Okay, so I decided to code all of the responses, the first and the second one, whether they were correct or incorrect, and then I would mine the third question for confusion expressed on the topic of the first or the second question. So this student would be right, confused about the second question. And this other student here would be wrong, no confusion at all. So let me show you the data. Using a traditional textbook on Laplace's law, on capillarity, the students who said they were confused, who actually said, I'm confused by capillarity, 44% got the question on capillarity right. Of the students who did not mention capillarity in the third one, only 25% got it right. What about Laplace's law? Of the students who said, like the second one that we saw, I'm confused about Laplace's law, 49% got it right. 21% of the ones who did not say that they were confused got it right. So the confused students are twice as likely correct. I know if you stop to think about it, that sort of makes sense. We're still all the way at the beginning of the learning process, right? The students who were not confused had not even begun to start to understand. They just read it like a novel. Sounds clear, just like a clear lecture might sound clear, but the material had really not sunk in yet. In later years, we used a different type of textbook where the students are forced to think while they read, because the text has sort of speed bumps in there where there are questions that they have to answer before they can continue to read on. That wipes out that difference, showing that if you force the students to think about it, you no longer have that. So, what does that tell us? That tells us that confusion is not necessarily a bad thing, right? I mean, you can be totally clear and have no confusion at all and be completely ignorant. In fact, there are a number of articles in the literature that have shown that. And this is especially true when your students have not been pushed to think. So, in conclusion, confusion does not correlate with understanding. And it's not necessarily the result of poor teaching. And the reason I think this is really an important message to get across is because I think this might be a huge barrier to the change in our teaching approach. When I gave my clear lectures, I got high evaluations. Students did well on textbook problems. They did miserably on the forced concept inventory. And I'm sure that each time they walked out of my classroom, they felt good. There was no confusion. But I think it was an illusion. When I switched to peer instruction, having them think in the class, they got many more questions, right? You have them think about something, and then hands would go up, but Professor Mazur, what about this? What about that? All of a sudden, the confusion has been elicited. I could see an instructor, I persevered in spite of all of the additional questions that I got, but I could see an instructor who says to me, Eric, I tried your approach, and now my students are much more confused, and see that as a negative side. Right? Whereas in reality, the students have just taken the first step towards better understanding something. So I think this is a very important message to get out that confusion is actually an essential step of the learning process. Right? Unless all you want to accomplish is that your students can regurgitate information or apply rote procedures. But my argument would be that's something computers can do. Right? We want our students to be able to do more than just rote memorization and the application of procedures. So I hope I've shown you how I think that classroom data can be vital to move us forward in education. There's a long list of people I want to acknowledge. And if you're interested in a copy of this presentation, it's already on my website. You don't need to write down. I'm against noting. Just go to Google, enter my last name, and hit this I'm feeling lucky button, and then you'll have a copy of Thank you very much.
Thanks. Floor is open for some questions.
I think I'm confused.
Yes?
Thank you for the presentation. This was great. I actually work in K-12 education, although I work internationally with universities. Can you speak up? Sure. I actually work in primary and secondary education, where I see things beginning to. So it's interesting because universities are suddenly starting to realize that they need to change the way they teach. Because a lot of university graduates keep graduating and not doing anything. So I'm just curious. It's a two-part question. Number one is I'm wondering for the university. Think of that. I go through a lot of universities and I still see them. If you looked at medieval France in 1200 and Australia, Indonesia, Singapore in 2012, everything looks the same. So I'm just wondering how much change are you starting to see among universities, and especially through academic, are there departments to help instructors change and faculty change the way they teach? And the second part of that question is there any move to go into K-12 education? Because those folks know pedagogy.
So two-part question. The first one is how much how widespread is the interactive approach to teaching, and secondly, is it starting to penetrate in K-12 education. So I've been relentlessly hammering for over 20 years on the same message, and I'm very happy, especially on this campus, to hear that quite a few of the classes are being taught interactively. And we recently had a first conference, International Conference on Peer Instruction in China, Beijing, a few weeks ago, and there were over 200 people from all across the globe, from K-12 education all the way through higher ed. There are books on peer instruction, astronomy, and chemistry, and physics, the first one that I wrote. There's the calculus, and so on. So yes, it's spreading. We still have a long way to go, because as you said, most of the teaching is still done by disseminating information based on the misconception, we learned it this way, therefore that's how students will learn. Now, in K-12 education, you get trained to teach. You have to be certified to teach. Likewise, to be an electrician, you need a certification. To be a lawyer, you need to be certified. To be a doctor, you need to go through many years of residency and training and certification. In academia, in higher education, simply by virtue of the degree that has been conferred on you, you're supposed to know how to teach. And as a consequence, we continue to do what our teachers did to us, and that probably can be traced back all the way to monasteries in the Middle Ages. So we still have a long way to go, but it's starting to find traction, including K-12 education.
I just wanted to ask, what traction have you had with your colleagues at Harvard? How many of them have adopted your methods? How many are hostile to your methods? Are you making progress in your...
So there's a French statement that says, "Nul est un prophète dans son propre pays." No one is a prophet in his own country. Interesting things happen. You see, at Harvard, we used to very much have the approach of every tub on his or her own log. Right? You go into your classroom, the door closes. What happens between those walls between you and your student? And most of my colleagues would be horrified if another colleague came in and watched what was happening there. There's no culture of learning from each other. The same way we have that culture in research. And in research, we would never think of doing research without first reading the literature, learning from each other, going to conferences, talking about what you're doing, and so on. So, but I benefited from that because I could experiment and do whatever I wanted without any interference with it. Then I started to get invited by other universities to talk about it. And universities like Berkeley, Stanford, you name it, started to adopt peer instruction. A few months later, one of my colleagues from my department goes to Berkeley, gives a colloquium, and hears, "Hey, we use your colleague Eric Mazur's method in our introductory classes." What is he doing? So they would come back to me and they would ask me, what is it that you're doing? So the message actually went from me to other universities and an impact. I'm happy to report that right now there are quite a few colleagues who are teaching interactively, not only in physics, but in statistics, in mathematics, in all kinds of different departments.
Whatever happened to meeting in the summer?
So, Professor Campbell was asking whatever happened to the meeting that we had in the summer. We had a chairman who really wanted to elevate the stature of teaching, and we had a meeting where Professor Campbell, Professor Lyman, and somebody from Stanford, I forgot who it was, gave presentations, and there were lots of brainstorming on interactive teaching. That has an impact. But as you may know, Harvard recently received a very major gift from the Hauser Foundation, $40 million. And those $40 million are being used all across the campus to improve teaching. And it's been just absolutely phenomenal to see what an impact that has had across the entire university, not only the Faculty of Arts and Sciences, but everything from the medical school to the law school, the business school, and so on, to start a dialogue of teaching and to really change, in a sense, the culture, to move away from that medieval monastic approach that we have to teaching to one in which we learn from each other, we talk about it, we think about it, and so on.
I just wanted to mention he's also, as an area dean, instituted Take a Colleague to Lunch. So if two colleagues get together and they go visit each other's class beforehand, right? And then the area dean is perfectly willing to pay for the lunch that they then have to talk about visiting each other's class.
Anywhere in the square, no matter Harvard, it's fine. But it only holds for
Just a couple more. First in the back.
Let's see if I can do without a microphone. You hinted at, in the topic of confusion, the aspect of the student evaluation. And often, there's these questions about, are the lectures clear? Is the lecture material, many of the questions are geared at, or, almost made for this style of teaching that there's evidence now it's not very effective. So for tenure-track faculty who get evaluated on this number, between 4 and so much, you need to be, what would you say, what's one to do if you're interested in, first of all, spending time in gathering data and reading about teaching and caring about teaching enough to change your method, and second, encountering student pushback in flipped classroom and all of these types of methods that they're not
Thank you for asking. I mean, look, I know for a fact that the way we evaluate our teaching is a joke. I got really high teaching evaluation. My students were not even learning the concept of force. Okay? I was just training them, like ponies doing tricks. I mean, they could solve problems, they could carry out triple integrals and so on, but they did not understand the physics. They could not transfer their knowledge, and if they were not majors, they forgot everything within 2 months after ending the course. So I think the way we evaluate our teaching is pretty meaningless. Right? If you stop to think about it, we not only don't we get any training, we've built a system where we get to evaluate our own teaching by, not only we teach, we set the exams too. I think that is pretty unheard of in any other human enterprise, right? That you control both the testing and the building too. If you stop to think about it, what is the true hallmark of the success of your students is to look much later at their career. How successful are they in their careers? And I think there's plenty of evidence that academic grades don't correlate very well with future success in society, in their careers. So that shows that we're not good at evaluating what constitutes good teaching. And I would advocate abandoning the end of semester evaluation, or maybe having it but not using it for the evaluation of promotion, and instead have a system where we basically learn from each other and observe each other. I wouldn't want to call it peer review, but something where we have a dialogue and we have communication between a community of teachers, which is totally lacking right now. Totally. The business school at Harvard is the closest to what I think is an ideal system. They have an official protocol for going and observing each other's classes, and it's ingrained in the culture of the business school. Each and every professor participates in observations of other professors and vice versa, and you talk about it. And it's not with the goal of criticizing each other. No, it's with the goal of learning the effective practices. And if you learn effective practices, things that are not working that well will automatically get dropped. Right? It's like an evolution towards a better approach to teaching. Now, pushback from students, that's a big difficulty, right? Because just as we have misconceptions about how we should teach, so do students have misconceptions about how they should learn. A lot of students who come to Harvard come from a system where they've done rote memorization, take the AP exam, right? I mean, you can get through the AP exam with pure rote memorization and rote procedure application. Right? They got a 5 on the AP, they think they're already excused from their physics courses, but Harvard ignores AP credit, so they have to take the introductory physics course again. They come to my class, I ask them all these questions that confuse them, what is their conclusion? Not, I don't understand physics. No, there's something wrong with Professor Missouri. So I have to spend quite a bit of time motivating them. I don't want to trivialize these problems. You're totally right.
Okay, very quickly, Al, and then Irving, you're last.
Two things. One, shouldn't these methods be involved in the education of teachers in secondary and elementary school? And two, the second question is, what about this vision to online teaching? How are you going to go and modify online teaching?
So one is, should these methods be used by teachers in elementary and secondary education? I would say if you look in kindergarten, if you look in any of the lower, K through 3, it is very interactive. Students are continuously interacting. You can't even stop them from interacting and learning from each other, right? But somehow, as students approach puberty, they're put in rows, facing the instructor. They are discouraged from raising their hand and asking why. It's the teacher who becomes the authority and the source of knowledge rather than, creating or constructing, I don't like that word very much, knowledge and understanding. So I think, yes, it should, but it already is. Unfortunately, we transition to a less effective approach as they approach university. Second one, online. Unfortunately, most of the effort with online teaching right now is simply old wine into new bottles. Videotape a lecture, put it online. Why would be watching the lecture online be better than watching in class? Okay, there's a benefit. There is a benefit. The benefit is that, for example, have you, Al, ever had a student in your class raise his hand and say, "Professor, could you please be quiet for 5 minutes? I need to think." I've never had that either. I would be surprised if anybody had. But online, you can actually pause and think. Or you could rewind and think. But still, it's focused on the delivery of information. And unless the student forces him or herself to think, it's just as ineffective as a lecture. So I think the move online will have to be paired with things that get students to think about. So you have to have questions.
For example, the Khan Academy.
Yeah, so we can move that later. Irving, very quickly.
Okay, so in the spirit of not throwing out the baby with the bathwater, or the professor with the bathwater, what of the medieval didactic tradition is worth preserving?
I would go further back. I would say, let's go to Socrates.
Socrates, thank you.
Socrates, already said, let's teach by questioning, not by telling. And I think he was completely right. Also, the interesting thing is the learning space. Is this type of learning space is basically copied from the Greek amphitheater. But the Greek actually never used the amphitheater for teaching. The amphitheater was used for performances with the sole purpose of focusing the attention of many onto one or the performance. If you look at an illustration of the School of Athens, you don't see people sit watching an instructor. They basically go, walk around, talk to each other, and learn from each other. So I think we need to forget about the Middle Ages. They were really dark in many ways, including education. We should go further back and re-adopt things that have been forgotten in a sense.
So let's thank our